In the years after the forced landing, the abandoned twin-engine bomber became trapped between ice, water, and shoreline. At an early stage, while the aircraft was in the water, an attempted recovery used a tractor and cable to drag the machine toward the shore. That rough effort kept major sections from simply disappearing into the lake, but it also damaged the airframe, cutting away the tail section and leaving the wreck exposed on the rocks. The choice was not a clean museum decision. It was a crude survival trade-off, imposed by terrain, ice, and limited equipment. That early movement fundamentally altered the preservation history of the machine. The aircraft was a Heinkel He 111H3, bearing Werk number 6830. Operated by the 5th Staffel, 2nd Gruppe, Kampfgeschwader 26, the bomber was forced down on May 15, 1940. The pilot executed a successful wheels-up belly landing directly onto the frozen surface of Lake Sitasjaure. The immediate outcome of this controlled impact was documented. The crew survived the event, although published summaries differ on the exact number listed aboard. After abandoning the aircraft and gathering what survival gear they could, the men moved on foot toward Norway. They did not simply vanish back into German service. They were captured by Allied forces near Skjomen and spent the rest of the war as prisoners of war. The aircraft was left on the ice as a remarkably coherent wreck. That early haul fixed the recovery problem that would define the wreck for decades. The central structure survived, but the tail was already gone, and the remaining airframe was no longer in a place where it could be removed cleanly. The surviving structure remained in a highly constrained geographic lock. Lake Sitasjaure sits in a remote mountainous region near the border, where vehicles could approach only to a point, and the final route to the wreck still required difficult foot access over rough terrain. The result was a new preservation problem. It kept the central structure visible and recoverable, but it left the aircraft in a place where ordinary trucks and cranes could not work directly at the wreck site. The target for modern recovery was not a complete airplane, but rather the extraction of the structurally coherent center section. This specific component contains the heavy inner wing spars and the original vertical bomb bay frames. These intact bomb bay frames serve as the primary anchor of the aircraft identity. They carry the manufacturing stamps, the primary load-bearing bulkheads, and the heavy aluminum extrusions that prove the physical integrity of Werk number 6830. Extracting this specific section required operating within the strict limits of the local terrain. Every piece of the aircraft had to be evaluated for its exact weight and transportability. The gap between the shore and the nearest usable road made every pound part of the extraction plan. Standard heavy trucks could not reach the aircraft. That exposed position held the wreck for decades, visible but never safely preserved. Ice, changing water levels, weather exposure, and human cutting all worked against the structure. The center section survived because its heavy bomb, bay frames, wing beams, engine mounts, and landing gear were too large and awkward to carry away by hand. Not because the shoreline was a gentle preservation environment. Its survival did not solve the extraction problem. However, the extreme isolation of the lake meant that bringing out the heavy center section required a completely different logistical approach. The initial 1940 patrols only needed to move the aircraft a few dozen yards to reach relative safety. A modern recovery operation required moving thousands of pounds of fragile aluminum out of a completely unimproved wilderness basin. The physical reality of the site presented a hard operational limit on what could be accomplished with standard ground equipment. Modern documentation narrowed the question from preservation to removal. The heavy center section could not be driven out, and it could not be dragged over the rocks without destroying the exact structural evidence the team wanted to save. How do you extract a heavy bomber from a rocky shoreline with zero road access? The structural survival of the bomber relied entirely on a physical trade-off between impact energy and surface friction. Prior to the landing, the aircraft sustained severe combat damage from Royal Navy Blackburn Skua fighters launched from HMS Ark Royal. The attack forced the crew to abandon the mission and make an emergency landing near the Swedish side of the border. The pilot faced an absolute decision. Attempting to put the bomber down among the surrounding rocks risked massive impact forces and certain structural failure. The lake offered the only surface that could turn the crash into a controlled slide rather than a single destructive blow. On wet, dense snow, the belly landing stretched the deceleration across a long horizontal slide. The lower peak load kept the central spars and bulkheads from fragmenting against the terrain. Once the kinetic energy reached zero, the immediate threat of destruction passed, but a long-term environmental threat began. The machine transitioned from an operational aircraft to an abandoned artifact. The subsequent 1940 decision to pull the wreckage onto the shoreline introduced a new severe constraint. That exposure lasted 68 years and opened the wreck to uncontrolled human contact. Exposing an airframe on a remote shore prevents the rapid freshwater corrosion found in deep lakes, but it subjects the site to decades of unchecked surface contact. Hikers, souvenir hunters, and local residents systematically stripped the airframe of its lightweight components. The unregulated access resulted in severe scavenging of the flight instruments, defensive weapons, and exterior aluminum skin panels. This process strips the historical detail from the outer shell while leaving the massive, forged internal spars perfectly intact. This produced the wreck's decisive physical divide. The cockpit was hollowed out, the outer wings deteriorated into open ribs, and the heavy center section stayed because it was too large, too awkward, and too far from any road to remove by hand. During the 68 years of exposure, the seasonal freeze and thaw cycle continuously acted against the lower fuselage. The aluminum resting directly on the damp rocks faced localized corrosion from trapped moisture. The key question was whether the primary load path, the heavy crossbeams tying the inner wings through the fuselage, had stayed high enough and strong enough to resist complete failure. Evidence discipline requires separating the initial combat damage from the environmental decay. The original combat damage inflicted by the skuas initiated the descent, but the later loss of exterior material came from several forces acting over decades: rough, early dragging, ice and snow loads, changing lake levels, weather exposure, and human scavenging. Assessing the airframe required a strict forensic accounting of what was actually left on the shore. The aerodynamic aircraft was gone. The recovery problem was now a skeletal core resting on uneven terrain. The structural integrity of this core was the sole factor that would permit any future recovery operation. The heavy internal frames had to be capable of supporting their own dead weight after decades of severe weather exposure. If the primary aluminum extrusions had crystallized or cracked under the shifting ice loads on the shore, the entire assembly would collapse upon movement. The physical evidence showed a wreck stripped of surface detail but still centered on a possible structural spine. The investigation therefore had two tasks: establish the identity of the remaining structure and prove that the central box could hold together under the tension of extraction. The defining structural feature of this bomber was its internal payload arrangement. The surviving central core contained 8 vertical bomb compartments set into the deep fuselage geometry alongside the inner wing structure. They were part of the heavy center section that made the wreck worth saving, but the identity case did not rest on a single dramatic stamp. It rested on the crash location, the known unit code 1H+DN, the documented work number 6830, the crew history, and the long record of the Sitasjaure wreck. When the bomb bay was later lifted away from the wing beams, investigators also found the number 2501 on a spar, a number once confused with the work number but later understood as something else. The evidence became stronger because the team treated those markings as part of a chain, not as a shortcut. After identity came the structural test. On site, they worked through the practical evidence in front of them: heavy wing beams, bomb bay structure, engine mounts, landing gear, rivet lines, corrosion, cut members, and collapsed sections. The surviving center section was not pristine. It was damaged, weathered, and partly stripped, but its main structural mass remained coherent enough for a carefully controlled lift, provided the airframe was separated into manageable sections and supported through its strongest remaining members. A complete site inventory required accounting for the heaviest missing components. The original aircraft was equipped with 2 liquid-cooled inverted V12 Jumo 211D-1 engines. Each engine produced 1,200 horsepower and represented a major point load on the forward wing structure. Investigators documenting the wreckage noted that the engine mounts extending from the inner wing spars were empty. The historical trail for those engines was uneven. Both engines had been removed by unknown parties. The left engine was broken down completely, leaving only the block at the crash site. The right engine remained more intact and was brought down from Sitasjaure in 1986 by Swedish aviation historians before passing through a complicated chain of custody. The 1986 engine retrieval fundamentally changed the physical limits of the modern recovery problem. Their removal changed the lift problem without solving it. Had both power plants remained on the nacelles, their point loads could have driven dangerous stress into the aging wing roots during a hoist. With the engine blocks gone, the mass was lower and the center of gravity more manageable. But the remaining center section still included the bomb bay, wing beams, engine foundations, and 2 complete landing gear assemblies. No published recovery account gives a precise weight for the central lift, so the safest conclusion is narrower. The missing engines made the operation more feasible, while the remaining structure still tested the helicopter crew's margins. The documentation now gave the operation a working baseline. The identity was locked down, the critical corrosion points had been mapped, and the center section was considered strong enough for a controlled extraction. The proof problem was over, the transport problem remained. How could the team physically bypass the rocks? The dead weight of the aluminum center section dictated a strict geometric limit against the maximum lifting capacity of the recovery team. By August 2008, the Forced Landing Collection and its Norwegian partners initiated the primary physical extraction of the wreckage. The site left one workable answer: a short helicopter extraction over the final wilderness barrier. With support from the Norwegian Air Force and a Sikorsky Sea King rescue helicopter, the team prepared the wreck over 3 days. They loosened wing coupling bolts, drilled out hundreds of rivets, separated the rear fuselage from the bomb bay, gathered loose parts into lifting nets, and prepared heavy straps for the larger sections. The smaller pieces of the aircraft were processed first. The torn outer wing remnants, loose structural ribs, and detached tail sections were gathered and bundled into heavy cargo nets. These lightweight packages were easily airlifted out of the wilderness basin. The primary challenge remained the massive center section. This unit contained the heavy inner wing roots, the main fuselage bulkheads, and the dense bomb bay framing. It represented the heaviest and most critical lift of the entire 2008 operation. Rigging this central core still required discipline, but the documented method was more direct than a museum-grade lifting cradle. The loose debris and smaller sections went into lift nets. The heavy center section was taken on thick straps, with everyone watching the coarse but simple sling that had to hold the aircraft's strongest remaining mass. The risk was obvious. If the strap geometry overloaded a weakened point, the wreck could twist or break. The recovery team relied on the strongest remaining structural members and on the Sea King crew's judgment to keep the load within safe margins. With the heavy strap secured, Sea King 189 moved into position. The helicopter swept between the mountain peaks, landed on a plateau about 100 meters from the crew, and then moved back over the wreck for the lift. Rotor wash whipped water into a curtain as the machine hovered over the shoreline. First came the easier lifts, then the real test began. One side began to rise, paused, and then the whole mass came free. The old Heinkel, code 1H+DN, made its final flight beneath the helicopter. When the pilot was later asked how heavy it had been, he did not give a number. The answer was simple: the load never went into the red. The decision to shift from helicopter extraction to road transport required a second handover, but it was not a clean transfer onto a paved highway staging zone. After the helicopter work, the team still had to bring in ground transport capable of operating in the mountain area. The following Saturday, a truck and trailer from Morups Åkeri came up from Falkenberg. The crew went back into the mountains to load the recovered sections using the crane mounted on the truck. Only after that loading step could the wreck enter the ordinary road transport chain. Transitioning to the truck and trailer introduced a completely different mechanical problem. The helicopter had solved only the final access barrier. Road transport meant supporting distorted, incomplete aluminum sections against vibration, bending, and local crushing. The crew used the truck-mounted crane to lift the recovered pieces onto the trailer and had to secure them through the strongest available structure rather than through thin skin, broken ribs, or fragile edges. At this stage, the operation became less spectacular but no less important. Every recovered section had to survive the road descent from the mountains. Once the recovered sections were on the trailer, the operation shifted from access problem to road survival problem. The transport crew secured heavy industrial tarps over the forward-facing sections of the exposed metal. This protective layer was necessary to shield the open internal bulkheads from highway debris and high-speed wind streams during the impending drive. With the flatbed loaded and the restraints checked, the wreck was ready for highway transit. Stabilization secured the aluminum, but what was the final destination for Werk number 6830? Leaving the mountains did not place the bomber directly into restoration. The next phase required specialized facilities and substantial funding. This extended holding period ended in 2021, when the American Heritage Museum officially acquired the airframe. The museum organization initiated a complex international transfer. By 2022, the heavy central core and the preserved wing sections were secured inside specialized shipping containers. The components crossed the Atlantic Ocean and arrived in the United States, ultimately reaching a dedicated aviation restoration facility in Florida. This relocation shifted the status of the airframe from a stabilized artifact to an active engineering project. In Florida, the recovery story became a reconstruction problem. The value lay in what could still anchor the rebuild, not in completeness. The outer shell, cockpit equipment, tail sections, and many skin panels had to be restored, rebuilt, or sourced from other Heinkel material. The museum objective is to create a highly accurate, full-scale static display in its 1940 configuration, not an airworthy aircraft. Museum restoration of a severely depleted airframe often requires mating original recovered structures with repaired or reconstructed sections from other sources. In this case, the Sitasjaure center section became the anchor for a composite restoration using surviving Heinkel structures, restored components, period-correct sheet metalwork, and careful alignment at the original attachment points. Earlier work on the nose section was done with limited drawings, photographs, sketches, and the practical judgment of experienced restorers. In Florida, the process has continued with deskinning, inspection, repair of internal structures such as stringers and longerons, reskinning with period-correct rivets, and restoration of original equipment where possible. The goal is accuracy and structural stability for display, not a guarantee that every part came from the same wartime airframe. The next decision was conservation rather than flight. Returning an aircraft of this condition to the sky would require stripping out the historic load-bearing metal and replacing the fatigued inner spars with modern aluminum extrusions. That process effectively destroys the original historical material to satisfy modern aviation flight safety regulations. That choice preserves the original load-bearing metal of Werk number 6830, including the forged aluminum frames that define the central box structure. Inside the museum, the artifact enters the strongest long-term protection it has ever had. Reduced humidity swings, limited pollutant exposure, regular inspection, and protective treatment under stable conditions. It does not end every corrosion process, but it converts wilderness decay into managed conservation. The integration of the various structural sections is progressing steadily. The heavy engineering work of mating the nose, the central spine, and the tail is establishing the definitive silhouette of the aircraft. When completed, this composite airframe will stand as a fully assembled, historically accurate representation of a frontline bomber. As of the latest public museum updates, the Heinkel He-111H-3 remains under restoration in Florida for eventual display, with no confirmed public completion date.